Okay, so last one here. This is not a p-series. Why? Because I can't rewrite it so it's in one n, right, all by itself, n to some p. It's not geometric. I don't see a common ratio or a first term. Integral test is not really applicable here because I can't really integrate that in its current form. The thing to look for in this, how could I make this be an integral test? If I made that squared, then I could do u substitution. And this 2n will go away, and then therefore it would be an integral test candidate. However, it's not. So my last test I have left is divergence theorem, or the nth term test. So let's just find the limit. That's a weird looking n, I apologize. The limit as n goes to infinity of 2n over n minus 2. You can do this limit two different ways. I'll do it both ways. I like to do it this way. I feel like this is the more mature way. This gives me the limit as n goes to infinity of 2 over 1 minus 2 over n. This guy goes to 0. I'm just left with 2, which is not equal to 0. So this diverges by the nth term test of the divergence theorem. We'll get back to that in a second. Everybody loves L'Hopital's rule because it's very easy, and in this case it is easy as well. As I plug in infinity, I get infinity over infinity. So I could L'Hopital it. I get n is going to infinity of 2 over 1, which is just equal to 2. And again, this is not equal to 0. So either method, I prefer this one up here, but if you want to use L'Hopital's rule, that's fine. So this diverges by the divergence theorem or the nth term test. So, what am I looking for here? You showed me that the limit is not equal to 0. In this case, you showed me it equal to 2. You can't just write down that the limit equals 2. You need to do some sort of either this algebraic trick here by multiplying 1 over n over 1 over n, or L'Hopital's rule to show me the limit is 2. Some of you have just been writing down that this is equal to 2. That's not sufficient. And then writing down diverges, and then one of the two different names, nth term test or the divergence theorem. Either one of those is sufficient.